Let's conclude our series on equations which become linear or separable as a result of a change of variables. And today we're going to be talking about a variety of differential equations that can be solved by what's called a linear substitution. Let me show you what I mean. So in the problems that can be solved by a linear substitution, you're looking for something of the form y prime equals a function of ax plus by plus c, where a, b, and c are constants. You're looking for a differential equation which, when you write it with y prime completely isolated on one side of the equation, the right side has the appearance of a quantity that looks like number times x plus number times y plus number. So if you see something that looks like this, y prime equals something containing number times x plus number times y plus number, the idea is to try the substitution. Set u equals that number times x plus number times y plus number. Set u equal to that entire thing. Once you have done that, then go ahead and try and change variables from y to u, and then once you've done that, try solving the resulting equation for u. Then go ahead and return the solution to being in terms of y. You have to be a little bit lucky in order for this solution technique to be possible, but let's see a couple of situations where this technique can be used. So for example here, very prominently, I'm seeing the appearance of this quantity number times y minus number times x plus number under the square root on the right hand side. So inspired by the appearance of this quantity, I'm going to set u equal to that number times y, number times x, plus number. And now I'm going to try and do a change of variables. The question really is what to do with y prime. So let's go in and take the derivative of both sides with respect to x to figure out what y prime would be in terms of u prime. If I do that, then the derivative of u with respect to x would be u prime. The derivative of y with respect to x would be y prime. But I have to be a little bit careful with these terms in the back. The derivative of 2x with respect to x would be negative 2. The derivative of 3 with respect to x will vanish. So as a consequence of that, y prime would be equal to u prime plus 2. So let's go back into the equation given to me, and let's substitute, try and get rid of all the y's and put u's in instead. So no longer y prime on the left, but u prime plus 2. No longer 2 plus the square root of this giant mess. That giant mess is equal to just u. So I'm going to rewrite this as 2 plus the square root of u. Now, behold what we have obtained. We have obtained an equation where the 2's on both sides can be cancelled out. And so we have u prime equals the square root of u. Now this is separable. In particular, it's actually autonomous. So we can bring the square root of u to the left, turn it into a u to the power negative 1 over 2, multiply that by u prime. And now if I integrate both sides, I get u to the power positive 1/2, I guess multiplied by 2, is equal to x plus c. Therefore, u to the positive 1/2 is equal to 1/2 x plus a newly refreshed c. And so u itself must be equal to 1/2 x plus c quantity squared. This is the moment where I need to translate the solution to being in terms of y. So scrolling back up, I can see that u was the same thing as y minus 2x plus 3. Let's go ahead and stick that information into this equation. So solving this for y really just means moving these other two terms to the right-hand side. Our solutions have the form x over 2 plus constant squared plus 2x minus 3. So we took an equation which was in the beginning quite a mess. It had y's and x's under roots and everything, but as a result of that substitution, we were able to turn it into a separable equation. As a matter of fact, an autonomous equation. Let's try it in a slightly more complicated example. Let's solve the ODE where y prime is equal to 1 minus x minus y divided by x plus y. Now if I just have a glance at this, I can see two possible candidates for the substitution. I could see, for example, it might be worth it to use u equals the constant 1, the constant negative 1 times x, the constant negative 1 times y. But I also think it might be possible to use u equals the constant 0 plus the constant positive 1 times x plus the constant positive 1 times y. Now, as it happens, I've gone ahead and actually tried the calculation both ways. One with the substitution u equals 1 minus x minus y, and one with the substitution u equals x plus y. Both of them will totally work. Both of them are completely fine in this problem, but I have a personal preference for the substitution at the top. It just turns out to make some of the intermediate calculations easier. So for me, having already done the calculations both ways, I'm going to go ahead and choose the first one. So with that choice, let's go ahead and try and rewrite this expression so that it no longer contains any y's and so that it only contains u's. So first things first, let's try and take the derivative of both sides of this equation so that we can get y prime replaced with u prime. So the derivative of u is going to be y prime. The derivative of 1 is just going to vanish. The derivative of negative x will become negative 1. And the derivative of y with respect to x is called y prime. So after a little bit of rearranging, y prime would be equal to negative 1 minus u prime. That's what gives us the left-hand side of our differential equation. Now on the right-hand side, we chose this value of u equals 1 minus x minus y, specifically because we saw it show up quite prominently in the numerator of this fraction. So this entire numerator is equal to simply u. However, what about the denominator? The denominator also contains an instance of y, but it's not something that can be so directly transformed into something containing u. To figure out the denominator, I'm going to show you what is, in my opinion, the most reliable way. I'm just going to take this relationship u equals 1 minus x minus y and isolate y. Then go into the denominator and replace the y with this expression on the right side. So x plus 1 minus x minus u. The two x's cancel out and I'm left with negative y minus u prime equals u over 1 minus u. So this looks like it's also going to be autonomous. First, let's combine all the terms that we can. Let's rearrange negative u prime is equal to u divided by 1 minus u plus 1. So if I combine those fractions, I get negative u prime equals u plus 1 minus u over 1 minus u. The u's in the numerator cancel out. Negative u prime is equal to 1 over 1 minus u. And therefore, if I flip the signs, u prime would be equal to 1 over u take away 1. Okay, so now let's go ahead and bring all of our u's to one side so that we can integrate both sides, the left with respect to u, the right with respect to x. Now looking at this equation on the left side, it does seem to me like finding an explicit solution is going to be absolutely miserable. So let's go ahead and content ourselves with an implicit solution. And using this implicit solution, let's replace the u's with what we know that they are equal to 1 minus x minus y. There are a few things that can be done to clean this up, just for the sake of our professional pride. For example, if I multiply through that negative, then I get a plus x on both sides of the equation, which can be cancelled out. And if I add 1 to both sides of the equation, then plus c plus 1 can be combined into a newly refreshed coefficient. So I can get something like y plus 1 minus x minus y quantity squared is equal to a newly refreshed plus c. But again, because there is a y which is outside of a square and another y which is inside of a square, solving this explicitly is going to involve some nightmare with like quadratic formula or something like that. So we're not going to be bothered and we're going to leave it at that. That concludes today's material, and it concludes section 2.5 about differential equations which can be transformed into something more manageable via a change of variables.